Can you hear me?
Yes.
Okay, great. So, welcome everybody, and warm welcome to Professor Schreier. I'm very happy to welcome him to this strange edition of IPROMO 2020. And it's very sad because we cannot be in here, sit on a table and have a beer, but okay, this year will be another kind of IPROMO, but hopefully it will be the only one. So, going seriously, I'm happy to welcome Hans, with all of his knowledge and experience. He will introduce to the principle of sustainable mountain development. So please, Hans.
Thank you, and greetings from the Wild West in Canada. I will stop the video and start with the presentation. We go here. So what I would like to do is introduce you to mountain watershed management, and just a brief introduction on what I do. I am Hans Schreier. I work at the Land and Water Systems program at the University of British Columbia. And I've been very fortunate to work in many different mountains in the world, including the Himalayas, the Andes, the Rockies, and the European and the New Zealand Alps. What I'd like to do today is introduce you first to watershed management. That will take about 40 minutes, and then we have a few questions. And then we obviously need to have a coffee break and a washroom break. The Italians need coffee and I need the bathroom. And then the second section will be on recent indicators of climate change in mountains. And then the next section is on how do we actually adapt to all these changes in climate. And then, of course, we also need to do something about the CO2 and reduce that. So I will try to give you some examples on what we can do. And then tomorrow, I'll tell you a little more about mountain tourism. I'll tell you a little bit about hydropower. And I introduce you to a Himalayan Andean watershed project. Since we have a virtual session, I will tell you something about virtual water and food security. And then at the end, we'll talk about how to conserve water and protect the water in the mountains. So let's start very briefly here. Mountains make up about 25%, as you know. It's about a fourth or so percent of population in the world. Here is a map of all the mountain areas in mountains, and you can see, unfortunately, I've never worked in the African mountains, but I will try to give you a couple of examples there too. So let's start. Why are mountains important? Well, in my view, they're the water towers of humanity. And also, you know, biodiversity hotspots. You know that it's a paradise for recreation, and it obviously has all kinds of social and spiritual values. But there are many, many constraints. Mountains are very fragile, as you know. They're hazardous. They have very low resilience to impacts, particularly climate change. And what happens in mountains can have a huge impact a long distance downstream in mountains. So mountain areas have low productivity capacity, and it's very difficult to get people in and out of the mountains. As you heard yesterday, how difficult is it to set up climate stations in these very remote areas? So there are many conflicts, and obviously there's a huge poverty issue, and this is why we have these workshops to educate people on what we should be actually doing. So this is a simple picture of where the water is. It's obviously all the water is in the ocean, Some of it is in the atmosphere and some of it is in the land. But if you look at this, huge, very small amount is actually on land. And the question I'm going to pose you to think about is, how much of the rainfall which falls on the terrestrial surface every year, how much of that rainfall ends up in the ocean every year? Have you ever given a thought about that? When it rains and hits the surface, the water runs off. Well, how much of that water on an annual basis, which hits the land, will end up in the ocean? You will contemplate that later on. Here is more of this kind of balance thing to show you where the water is. The numbers tell you the the gigatons of water in the ocean and in what is being transported. But what I would like you to not pay attention to is soil moisture. We have 17 gigatons of water in the soil. This is far more than all the water in the rivers and all the water in the wetlands. And I don't think anybody has ever thought about the water in the soil. And I want you to remember that if you change the soil, you change the water content. And so this is a very, very important concept in the mountains, because mountains have very shallow soils and they can store a lot of water. And if we disturb them, it's going to be a reduction in storage. Now, just to make it a bit more interesting, we want to put a little bit of color into water. So we call water blue water, green water, white water, brown water, black water, and virtual water. You think I'm totally crazy by telling you this, but let me show you what I mean by that. You know the hydrological cycle. You know that precipitation falls, it evapotranspires, it goes into rivers, it goes into groundwater. So the blue cycle of the hydrological cycle is the precipitation which falls on the land, flows into rivers, reservoirs, and lakes, and percolates into groundwater. That's the water which we use, and that's the water which we manage. But then we also have the green cycle, and this is part of the precipitation which hits the surface, hits the trees, goes into the soil, and is then evapotranspired back up into the atmosphere. Have you ever thought how much water goes to the green cycle and how much water goes to the blue cycle? Remember, we use the blue cycle for everything we do, from drinking water to irrigation to everything. And if you look at this, all the precipitation falling on the land, 65% goes into the green cycle, and only a third goes into lakes, rivers, and groundwater. This is what we manage. This part, we don't manage very much. And remember, about 80% of the agricultural land produces about 60% of the food, and this is green water. This is not irrigated water, because irrigated water is blue water, and then we mess up the blue water, pollute it, so we then have gray water, and then we could actually reuse gray water and irrigated water for agriculture. And then if you go up this way, you end up in the white water business. This is the water which evaporates. So keep that in mind. This is a simple way to show you how important it is to think about blue water versus green water. So mountains obviously are a big reservoir of water. It depends on the elevation, it depends on the climate regime, in the topography, the vegetation, and the land use activities. But usually we think water comes from most parts of the world from mountains. So Daniel Viviroli did a very interesting study many years ago, and he looked at how much of the watershed is in mountain areas. So the bars, which I'm showing you here, is the percent of the watershed which is in mountains, and the blue dots, which I'm showing you here, is how much of the water in the basin actually comes from that part of the watershed. So if you look at the Colorado, the Rio Negro, the Amu Darya, and the Nile, they get almost 90 to 100% of all their water in the lowland from the mountains. The other ones in the Euphrates, the Indus, and so on, they have a relatively small amount of area in the mountains, but still contribute quite a large amount. And then, of course, some of them, which are pretty flat mountains, don't contribute a lot. But what is even more important is not that they produce so much water, but when do they produce that water? What I'm showing you here is a precipitation map of Europe. The blue part is the high precipitation, and the red part is the low precipitation on an annual basis. So if you look at the European Alps, which go through here, most of these have high precipitation. And so when you look at the European Alps, 4 river basins drain the European Alps: the Rhine River, the Danube River, the Po River, and the Rhone River. This is the percentage of the river basin which is in the Alps. So the Rhine has only about 15% of the water in of the area in the mountains, but produces about 35% of all the discharge of the river down in Holland. If you look at the Rhone, 23%, but almost half of the discharge. The Po, for our Italian friends, only about 35% is in the mountains, but produces half of all the water in the downstream direction. What is even more important is, when do we deliver that water? So the mountain areas are small. The amount for an annual basis is relatively medium, but the summer contribution is really when everybody uses more water, when everybody requires more water. This is when all these mountain areas, particularly those which have a lot of snow and a lot of glaciers, particularly the glaciers, produce that water at the critical time of the year in the lowland. So if you look at the big river basins in the world, from the Ganges, the Nile, the Yellow, the Indus, the Niger, and the Mekong, here is the estimated population in these river basins. So in the Ganges, we're talking about 500 million people. A third of the river basin is in mountains, produces about 65% of all the water for all these people who mostly live in the lowland. And this is just giving you an idea how much discharge in cubic meters per annual average. This is the average, that's the maximum, the minimum. And you look at these numbers and they're incredibly high. So that gives you a bit of an idea of importance of these mountain regions in terms of water supply. Now, we often classify the various mountain areas, how much water do they produce for the people who live in these basins. So if you look at this, the categories which they use in the UN is if a river basin or a country has less than 500 cubic meters per person per year, that means you're in absolute scarcity. And that is the case in many, many of the MENA countries, the Middle East and North African area. Water scarce countries, we say if you have 1,000 cubic meters, you're scarce, or less than 1,000. If you have 1,700 cubic meters, you're still stressed. And if you have about 2,500, that means you're seasonally stressed. So we can apply this on a national basis, but we can also apply it to a river basin area. And so if you look at the Yellow River in China, they're obviously in the absolute water scarcity situation. And this is why the Chinese now are trying to divert the Mekong, the Yangtze River into the Yellow River. But if you look at the Yangtze River is seasonally stressed. So again, this creates all kinds of complexities. And so if you look at the South Africa situation, the Orange River in South Africa, that's water stressed. And you know this because 2 years ago, they almost ran out of water in Johannesburg and Cape Town. So that gets me to the Himalayas, and what I want you to show, I wanted you to see is mountains are incredibly variable. And this is where we have some real problems trying to make predictions. So if you look at the Himalayan mountain range from Myanmar all the way up to Pakistan, if you look at the amount of annual precipitation in Bangladesh and Cherrapunji, you get 11 meters of water per year. And if you go all the way down up to Leh in the Karakoram, you get 115 millimeters. So compare that to 11 meters. And you can see the variability is huge depending on where you are in terms of elevation, in terms of aspect and slope. But it's not only the annual precipitation which is variable. This is the 24-hour precipitation. And if you look at here, we get the highest one-day precipitation was 39 millimeters. That's virtually nothing. And then you go down to Cherrapunji where you get almost a meter in one day. So think of it, look at your height. Let's say you're 180 meters, a meter 80 tall, and you get almost a meter of water in one day. That comes up to your belly button. So that's a real problem. The other thing you need to remember is when did this water occur? So in the Himalayas, we have the monsoon season from May till August. And the numbers I'm showing you here is the percent of the annual precipitation which occurs during the monsoon. So almost in all of these places, about 70 to 80% of all the rainfall per year occurs in these 4 months, which then means in the summer, in the dry season, you're going to have very, very little water. And this is easily visible from space. If you look at the wet season, this is the Ganges River, and you can see it's all flooding down here during the monsoon season. And during the dry season, the river is extremely slow and very stressed. Here is this is the Terai, and this is the Middle Mountains, the Sivalik Mountain. Excuse me. This is not just in the Himalayas, this is also in the Andes. In all mountain areas we get this variability. I just wanted to show you an example from Peru. If you look at Lima, which is somewhere down here, Lima gets 5 to 10 millimeters of rain per year. Think of that. 10 millimeters, that's 1 centimeter of rain per year. That's a complete desert. And if you go up into the tropics in the Amazon area, they get up to 3,000 millimeters. So within the same country, they have a huge precipitation range. So if you look at about a third of all the population lives in coastal regions, so about 13 out of 35 million people in Peru live in a coastal area. And so depending on the situation, the dry season is really the critical part for the lowlanders, and the mountains play that key role. So why would the runoff from mountain ranges be so variable? Well, it depends on many factors. First of all, how much change do we get in precipitation to year or day to day? How much change do we get in snow accumulation? And obviously that affects the runoff. How are the glaciers changing? And that is particularly important because big glaciers produce of summer water. But small glaciers, when they get too small, all of a sudden they stop doing that. And we have problems predicting when that point will happen. We call this tipping points. And then, of course, the runoff from river also depends what we do, because if we build a lot of reservoirs and dams, we stop some of that water from flowing, and then we release it at different times, which means we change the hydrological regime quite dramatically. And then, of course, we extract water for domestic and irrigation parts. We change the vegetation, which affects the stream flow, like logging and fires. And then, of course, the groundwater, which is being recharged by the precipitation, we use that for all kinds of purposes. And in the mountains, we use it primarily for mining. And some of these mines, particularly in dry areas like Chile in the Atacama Desert or in Peru, that's going to be a very important part, which means if we use all the groundwater and the groundwater doesn't feed the streams, we virtually have no water flowing in those streams. And then, as I mentioned, soils are critical. And if we compact them, we lose storage capacity. And so the changes in the soil surface, whatever we do in terms of land use, impacts the runoff of your streams. So the McKinsey Corporation did some projections for the world, and they showed the in 2010, about 69% of all the water was used for agriculture. And so this is the 2005 situations in terms of billion cubic meters. The green is for agriculture, the red is for urban, and the blue is for for agriculture. I screwed up these colors. This should actually be green and this should be blue. So this turned out, I'm colorblind, so keep that in mind. So we need to start looking at these mountains in terms of watersheds, because this is the only way we can actually do some quantitative assessment. So the very first thing we need to do is we need to look at the topography and delineate the watershed by looking at all these little streams where they end and say, where is the watershed divide? And this makes up the boundary. So the best way to do this is, first of all, to delineate the area and look at the topography, and then you can add your image to show the watershed and the land use in it. But now we have GIS, Geographic Information Systems, and this is the key to managing watersheds anywhere in the world. And the best thing to start is to do, first of all, a digital elevation model. So the first thing you want to do is look at the topography and then generate what I call an elevation slice map. So these are that's the low elevation, that's the high elevation. So you can see, we can then determine how much areas are in each one of these elevation categories. We can also produce an aspect map, because as you know, in mountains, north-facing slopes behave very differently from south-facing slopes. So you can actually make an aspect map from the digital elevation model. And you can also make a slope map where the blue and green areas are flatlands and the red and yellow areas are very steep sloping different categories. So GIS is really the best way to do this. And we're now at the point where we can do this using all kinds of imagery from space. And then we can actually do the land use information. And then we can actually add all kinds of information from climate and hydrological information. Like in this case, it's the temperature versus the precipitation. Or you can look at time series from 1967 all the way to now, and the mean discharge in the river, and you can see the trend, the variability and the trend. So this is the basic information for good water management. You need to remember there's some advantages and some disadvantages of using the watershed approach. In my view, the advantages outperform the disadvantages by about 80%. So the reason why we use the watershed approach is because we're delineating natural land units. It's ideal for monitoring because we can measure how much comes in terms of water and how much goes out and how much is recycled within it. And we can use all kinds of scaling. We can use a mini watershed, a regular watershed, or a river basin to do that. We can also then do mass balance studies, not only for water, but for nutrients, for everything we'd like to do, because most of the nutrients are recycled in water. And in plants and water, so we can actually do a very nice balance for that thing as well. So we can do input output, and we can look at cause and effect, particularly in pollution. We can then say, well, if we get a pollution level in the outlet of the watershed, we can trace it back on where it's from. We can also then look at the impact of different land uses, the link of land to water, and we can facilitate a system analysis. It allows us to look at cumulative effects, because what we could do, we could look at each mini watershed and say, how much is each mini watershed contributing and how much is the cumulative effect? And we can look at the interaction between soil and water, and we can look at diffuse sources. So it's a science-based decision-making process. It's very effective for management, and it allows you to actually make adaptive management as we understand how the problems operate in these systems. However, there are some difficulties, and the difficulties are that we need long-term monitoring, and as you heard yesterday, that is a very expensive proposition, not only to set up climate stations, but think of all the water quality monitoring which we need to do. And then you need to ask yourself, what different chemicals and contaminants are we going to monitor, or how many nutrients are we going to monitor? So that's quite expensive. So we also, in terms of doing this work, we need some undisturbed control sites. Often in the past, we looked at a paired watershed where one was undisturbed and then next the adjacent one, we did some experimentation like changing the logging system. But this is no longer possible now because there are virtually very few undisturbed comparable watersheds. Boundary issues. The real problem is if you want to use socioeconomic data in a watershed basis, we have huge problems because the political boundaries never match the watershed boundaries. The only exception to that is New Zealand. The South Island of New Zealand actually changed their political boundaries to match the watershed boundaries so that we actually know how many people actually live in each watershed. And so extrapolation is a problem. If you do all your work in one watershed, it is very difficult to extrapolate that to another watershed because all the factors are different. And so that is a bit of a challenge. And then, of course, the processes change over time. Now, the other issue is at the scale. We always think that all the processes are linear, and process make upstream, downstream scaling quite difficult. And then finally, air pollution, CO2, climate change, and all that stuff doesn't recognize boundaries, which means we can try to control everything in our watershed, but we can't control the air pollution. We can't control the CO2 which comes into it. And so those are the big challenge in watershed management. I hope that gives you a bit of an idea on some of the things we have to Now, the most important thing we will talk a lot when we talk about adaptation is it's not just the climate. You know, people are now completely preoccupied with climate change as the main driver of all the changes which are happening. But you also need to consider the land use. And in some cases, I would argue that the changes in land use might be more important than the changes in climate. The example I can give you, if you look at a city where we have paved everything and made everything impervious, we changed the hydrological cycle dramatically, which is probably more important than the climate change. But again, it depends on the land use, so we need to consider both of these things, and we need to start working together. If you look at all the climate change people, they almost all focus on climate data. They very rarely start looking at the changes in land use. And that's one of the criticism I have with the IPCC. They're now starting to consider the impact and the interactions between climate and land use. This is probably the most important diagram I want you to consider and think about. What I'm showing you here in green is how much of the precipitation which lands in your watershed is evapotranspired in green, how much runs over the surface, how much goes into the soil in yellow, and how much goes into the groundwater which seeps through the system. So this is what happens in a forest. About a third of all the rainfall evapotranspires by the plants. And only a very small amount actually runs off the surface, because if you're in a good forest with a big soil organic layer, very little of that water actually goes directly into the stream. It seeps into the soil or into groundwater and might get into the river. If you now change your land use from forest to pasture all the way to urbanization, look at the red area. This is how much water runs over the surface and creates all the flooding and all the peak flow. Look how little happens in the forest compared to what happens in the urban environment. So keep that in mind when you think about how land use change affects the water flow in rivers. Now I'm going to show you some horrendograms. That's just to overwhelm you. But the idea behind it is I want you to understand the complexity of every land use on water. This is what we do in the urban environment. We create stormwater runoff, we create domestic water waste, we create industrial discharge, accidental spills, solid waste, and we also have impact from air pollution in cities. And these are the kind of pollution problems which are created in urban environments, and you can see the complexity, and they all interact. One of the interesting things to me is when you talk to the urban engineers, you will find that there's a group who treats your drinking water to make sure it's safe. And then there's another group who treats your wastewater. Well, they also treat the water in most places. Well, these two groups very rarely talk to each other because they're all in compartments. And we need to start interacting so that they can actually share experiences which might be helpful to one another. So look at the complexity in urban environment. Another horizontal is the complexity in agriculture. We do agriculture intensification, which means we irrigate, we add huge amounts of chemicals, we create salinity, we create organic matter, we have drainage issues, we leaching issues, nutrient imbalances, soil compaction, acidification. All of these affect the quantity and the quality. If we move on to forestry, even forestry has an impact on water because we harvest, we create changes in the flow, we change the stream temperatures when we do a lot of big logging, we create all kinds of sediment problems, nutrient issues, pesticides, and habitat changes. And we not only do it with harvesting, we plant trees, that changes things as well. We create a lot of roads to get into the forest, and we create these roads in mountains, which are very hazardous, creating lots of sediments and stuff, and so on. And then we go to mining, and mining is also pretty nasty because they have all these different activities, and these are some of the impacts mining does in river basins. So the point I'm trying to make with these horrendograms, if you would put all these 4 diagrams together, you get a plate of spaghetti. Because what that means is this is getting so complex that we have huge difficulties trying to reconcile who is actually responsible for some of the water pollution or for the lack of water which comes out in the lowland. So keep that in mind. It's a very important part of what we do. And this gets me to governance. And I would say this is probably the most difficult resource to govern. If you look at all the resources we have, water is the most difficult to actually manage. Why do I say this? Everybody has an opinion about water, and very few people have knowledge about water. And the reason why I'm saying that is, if I ask you, what does your water which you're drinking right now, how does it taste? You will tell me, well, it tastes good, or you tell me it doesn't taste very good, and then I ask you why, and then you have a real problem telling me exactly why it doesn't taste very good. You can speculate, but you probably don't have enough information. So this is just showing you all the agencies which manage water, and they all operate separately. And then here are the institutions which govern the monitoring, and here are the institutions who regulate water. And so you can see trying to get a real integration of all this is not very easy. And then gets to the traditional approach. What we have been doing in the past is these are the things we have been doing, and what I'm suggesting we should be doing now is doing all of these, and I'll go through. I mentioned all we use is blue water. We manage the rivers, we manage the reservoirs, the groundwater, and so on. And now we need to start looking at green water management. How can we improve the way the rain falls onto the vegetation and into the soil and back up into the atmosphere? We do some really stupid things. We grow rice in Southern California in a desert, which is the most water consumptive crop, in a dry environment, which means they almost have divert rivers from mountains in order to maintain this, or use groundwater in an unsustainable way. Every time we have water shortages, everybody says, well, let's look for some new supplies. We are now at a point where there are very few possibilities for new supplies. So what we need to do is control the demand. We have tried to drain everything. You know, people, when you have a house or if you live in a city, you don't want to get flooded. So that means we have told the engineers to drain everything as fast as possible away from your house and from your roads and from your parking lots. And now what we're saying, maybe we should try to infiltrate to soils, to store it temporarily, and so on. Most of the irrigation, particularly in mountains, is flood irrigated, and we need to do much more efficient irrigation. Water for human use, we have basically decided we are the species which should use all the water. And now we say, well, we need to leave some water in the river for environmental services. We focused almost everywhere in point source pollution. We know where an industry is or a sewage treatment plant is. And so we focused on their pollution, and that's relatively easy to monitor because we know where they are. We often know what they produce. But what is far more important is what I and you produce as a very small amount, the non-point source pollution. Each individual's problem is not an issue, but it's the cumulative effect of non-point sources. If you look at regulations of water, we regulate every single chemical, but we never look at the cumulative effect. My example to this is, if you're old and sick and you get prescription drugs, they give you 5, 6, or 7 different drugs per day. The individual drug does something good for one purpose, but multiple drugs have all kinds of interactions, which is probably a real problem. And this is the case, of course, in a watershed as well. So we usually do end of pipe treatment. You think of, you flush your toilet and it goes into the sewage treatment plant at the end and they treat it. So what we now need to do is control the pollution source before it gets into the river, and this way we don't have to treat so much at the end of the pipe. And then intensification and soil compaction, as I mentioned before, is critical, and we need to minimize the soil compaction so that we can store as much water in the soil. And then when we create impervious surfaces, we need to think about delay, detain, and infiltrate. So those are the kind of interesting things we need to think about when we start looking at innovative actions. So the real issue is one of equity, because the complexity shows you that everybody wants a part of the water cycle and everybody wants more. And how do we actually allocate enough water for drinking, for sanitation, for irrigation, for ecological services, and animals and fish? And this is a very contentious issue, and obviously this is something we need to discuss. And I'm not prepared to give you any ideas about this because I'm a scientist and I don't know anything about social science. So why do we need water conservation efforts? Because we need to maintain ecological services. We need to limit uneven distribution. The costs of all the treatment are increasing, the demand of exceeding the supply, and high, and all of these activities obviously requires more water, which means we need to save water by being much more efficient in the way we use it. So how do we cope with climate and land use interactions, and how does it impact water? We need to look at both the land use and the climate change. And so what I will be doing in the next session is I will focus on the climate part, and I'll show you some ideas on what is happening in the mountains in different parts of the world. And then later on, we look at adaptation and reduction in sequester of carbon. So that's the first part. If you have any questions, I'd be happy to answer them. And we will obviously take a short break so that the Italians can have their cafecito. And I will use the washroom.
Okay, thank you very much, Hans. Concerning coffee for Italians, it should be the fourth one in the day. There is already a questions from Kika Bradford there, and she would like to have a recap concerning the difference between green and blue water.
Okay, so remember, precipitation falls onto the land. What happens once the precipitation falls on the land, it can either go back up into evapotranspiration or it can flow over the surface. And when it flows over the surface, some of that water goes into lakes, rivers, reservoirs, and seeps into groundwater. That is, we call the blue water. The green water is the precipitation which doesn't flow over the surface. It hits the surface, the vegetation, and the soil, and then the plants pick it up and evapotranspire it. So that water recycles within that cycle, and that's the green water. Does that help you understand?
Yes, she thanks you for the answer. Okay. If there are let's say 2 more questions, and then we can have a 5-minute break, and then we can go on. You can also raise your hand and I give you the word, so you can ask directly to Franz your question. Don't be shy.
I probably bored you because you probably know all of these things, so that's why you don't have any questions.
Okay, there is another one. Land use intensification is a reason for climate change. Can irrigation lead to loss of water in drylands?
Yes, of course, because if you use groundwater, you irrigate with groundwater, you evaporate that water, which means you got a limited resource. And if you don't get enough precipitation, which doesn't recharge the groundwater, you're going to deplete the groundwater and then you end up with no water. I will show you some examples of that in the Middle East tomorrow.
Okay, thank you, Hans. One more question. Okay, I guess session 1 is like an icebreaker, so they have to warm up a little bit. So okay, I suggest to make the 5-minute break now, and when you are ready, Hans, just let us know. I'm as you know, we are recording the session, so I'm stopping now. And when you are back, just advise me, and I start the recording again.
Okay.